Hello everyone. Today we are discussing about the NQ's problem using backtracking. The NQ problem is one of the best problems used to teach backtracking and of the course equation. Backtracking is a general algorithm which finds or complete solution to a problem by building over partial solutions. In this process, the problem might reach to a partial solution which may not result into a complete solution. Such partial solutions are effectively rejected by the backtracking algorithm. What is backtracking? Backtracking is finding the solution of a problem whereby the solution depends on the previous steps taken. In backtracking, we first take a step and then we see if the step taken is correct or not, that is, whether it will give a correct answer or not. And if it is, does it, then we just come back and change our first step. In general, this is accomplished by regression. Thus, in backtracking, we first start with a partial subsolution of the problem and then check if we can proceed further with this subsolution or not. If not, then we just come back and change it. Thus, the general steps of backtracking are: start with a subsolution, check if the subsolution will lead to the solution or not, and if not, then come back and change the subsolution and continue again. The classic case of NQ problem. In this problem, you are given an empty chessboard of dimension n into n. The task is to safely place n queens, one in each row such that they cause or harm to each other. The basic idea is mentioned below. Start from the first row, select a column, and if it is empty, well within the limits of the board and in no immediate danger, then place the queen in the cell. Proceed to the next row. Two conditions might occur, that is, all the rows are safely filled. Somewhere down the line, one of the queues can't be placed in a row. Or we need a backtrack because a decision was wrongly made in the past. NQ's problem. NQ's problem is one of the most common examples of backtracking. Our goal is to arrange NQs on an n into n chessboard such that no queen can strike down in other queen. A queen can attack horizontally, vertically, or diagonally. So, we start by placing the first queen anywhere arbitrary and then place the next queen in any of the safe places. We continue this process until the number of unplaced queens becomes 0 or no safe place is left. If no safe place is left, then we change the position of the previously placed queen. Let's test the algorithm on a 4x4 chessboard. Using backtracking to solve NQs. This picture shows a 4x4 chessboard and we have to place 4 queens on it. So, we will start by placing the first queen in the first row. Now, the second step is to place the second queen in a safe position. Also, we can place the queen in the first row. So, we will try putting the queen in the second row this time. Let's place the third queen in a safe position somewhere in the third row. Now we can see that there is no safe place where we can put the last queen. So we will just change the position of the previous queen, that is, backtrack and change the previous decision. Also, there is no other position where we can place the third queen. So we will go back on more step and change the position of the second queen. And now we will place the third queen again in a safe position other than the previous place position in the third row. We will continue this process and finally we will get the solution as shown below. Backtracking algorithm. The idea is to place cues one by one in different columns. Starting from the leftmost column, when we place a cue in a column, we check for clashes with already placed cues in the current column. If we find a row for which there is no clash, we mark this row and column as part of the solution. If we do not find such a row due to clashes, then we backtrack and turn false. Conclusion. Most of the time problems of backtracking can be easily identified by the following features. It will have a lot of solutions. You will get some intuition that not all solutions will solve the problem and you might have to go back and change something. As each step, you have to verify the integrity of the solution, like if it is safe to move, etc. Based on the future steps, the present choice is considered a valid choice or not, and no need to worry about the backtracking part. The recursion step takes care of it. Thank you.